Hello and welcome to a Black Hat Arsenal talk. Today's topic is around firmware analysis, especially firmware analysis with EMBA. EMBA stands for Embedded Analyzer, and it is a fully automated security and vulnerability analyzer for firmware of embedded devices. And the best thing on EMBA is it is open source. So right after our talk, you can go straight to our GitHub repo, download EMBA and start analyzing firmware. Find weaknesses, find vulnerabilities, and at the end, making the Internet of Things a little bit more secure. So my name is Michael Messner. I'm a penetration tester at Siemens Energy. During my daily business, I perform penetration tests on critical systems and environments. This is the area where we developed EMBA and where we are using EMBA on a regular basis. So today's environments are more and more connected. Think about your smart home at home. Or think a little bit bigger about an OT network, which means operational technology network in a big company. Think about your smartwatch. Your smartwatch is connected to your smartphone is connected to everything else. If you are going to work by car, you're passing traffic lights. These traffic lights are connected. Your car has a huge amount of embedded devices included. These are connected and you get the updates over the air via the internet. The power grid completely connected, which means critical infrastructure is connected, power plants are connected, and so on and so on. So the thing is that the bottom layer of all of these connected devices are the little gray boxes. Yeah, they are not often little and not every time gray, but these are embedded devices, and these embedded devices are the base. And on these embedded devices, there's running an operating system. This operating system could be a full-blown Linux distribution. Most of the time, it's more optimized. For example, a stripped-down Linux system. Or some kind of real-time operating system, like a VxWorks. Or something handmade, something special, bare metal. The term that we are using for all of these operating systems is firmware. And according to Eclipsium, they've released a report a while ago. Firmware is the most exploited vulnerability category over the last few years. And according to a report, the Microsoft Digital Defense Report, which was released a few weeks ago, around 32% of their analyzed firmwares have more than 10 known critical vulnerabilities. And 4% have known critical vulnerabilities which are known for the last 6 years. And so from our perspective, firmware security at all, and especially firmware analysis, is more important than ever before. So now let's think about the typical use case of a penetration tester. You have on the one hand the real device, so you can perform live tests on the device via the network, for example. And on the other side, you have the firmware. So you can move from a black box only approach to a more gray box approach. And if we think about the firmware analysis, we start with a binary blob. So first things first, we need to do some information gathering. What is this binary blob? Do we have areas with clear text, plain text things in it? The next thing probably is we try to extract things from this binary blob. So probably there is a hidden Linux operating system, a Linux file system in it. So we need to extract it out of this binary blob. And if we extract the Linux file system, we now can do some further analysis with it. We can find interesting stuff, password files, for example. We can find binaries, libraries, configuration files, and so on and so on. We can do some basic analysis with it. We can combine our find commands with some grep, and so on and so on. In the meantime, we probably will do a lot of research about the things that we have seen now on how to proceed and so on and so on, which takes a lot of time. And we will load things into IDA or Ghidra, and at the end, we hopefully find some interesting areas, some weaknesses, configuration issues, or vulnerabilities. So first things first, we need the firmware. This is more or less the manual task that you need to fulfill. You need a binary blob from the vendor, from the hardware somewhere, and then you need to feed it into EMBA. You can start EMBA with only one parameter. Usually you probably will use 3 parameters. We will see it a little bit later in the demonstration. Then EMBA will start extracting the firmware. After the automated extraction process, EMBA will start analyzing the firmware. This is more or less the heart of the whole firmware analysis. You're using different analysis modules from EMBA, and EMBA will give you at the end a quite interesting overview of the complete firmware. And you get an HTML report as output. So also the reporting that every penetration tester loves, really. The reporting is automated and you can perform further teardowns within your browser. But now, before we are starting with the automated area within EMBA, let's take a quick look on how can we get access to the firmware by itself. So there are different possibilities. For example, you can go to the website from the vendor, you can start digging into the website, and hopefully you will find some firmware updates on this website. You can download it, feed it into EMBA, and you're good to go. If you do not have access to the firmware from the vendor website, or it's behind a paywall or something else, probably there are no firmware updates available currently. Then there are different other possibilities. You can, for example, use some shell access via Telnet or SSH or some serial interface to extract the firmware. You can use vulnerabilities like a command injection vulnerabilities. If you're able to identify a command injection vulnerability directly on the device, you can probably exploit it and extract the firmware. And finally, you can do or perform hardware attacks. You can use a serial interface. You can use debugging interfaces like JTAG or SWD. If you find, or if usually the firmware is stored on a flash storage and transferred from the flash storage to the CPU during the boot up process. So you can sniff the communication and extract the firmware from there. Or at the end, you can start invasive attacks like disordering the flash. Usually on the flash chip, the firmware is stored unencrypted. So then you can extract it and you have access to the firmware blob. But this firmware blob is more or less some kind of binary blob now. So you need to start digging into it. You can, for example, as mentioned before, use established extraction tools like binwalk or armblob. And in an ideal world, you then have some Linux root file system extracted, and you can start your commands. You can start find, you can start grep, and so on, or EMBA. But as these extractors are sometimes quite limited, we introduce different extraction modules into EMBA. So first of all, we have an extraction classifier. This extraction classifier tries to identify interesting parts within the firmware and uses the right extraction module afterwards. So for example, if we are able to identify a zip archive or a target set, then we are just extracting this. It's a little bit different on some interesting or special file systems like ext file systems or UFS file systems. We can mount this file system and copy the files from it. The same on VMware images. As we get a lot of VMware images during our daily business, we need a valid extraction mechanism for it. So mount it, copy it, and you're good to go. Then there are a lot of vendors or multiple vendors that are trying to hide the firmware from us. So they're using some kind of encryption mechanisms. But sometimes the keys are just lost or leaked. Sometimes the whole encryption mechanism is broken, and so we try to implement these things that we found in the internet within EMBA so that we are able to extract it. And finally, some special things like firmware from special vendors like AVM. We are using tools for this. And at the end, if none of our handmade extraction modules catched it, we are falling back to a binwalk extraction mechanism. After all of this, we try to find or identify a Linux root file system. If this works, so if there is a Linux root file system now in the extracted data, then we are good to go. We can start up our analyzer modules and they are doing the job. But if we do not identify a Linux root file system, we are now starting up the deep extraction mechanism, which means that we are walking through all of the files within, that we have currently extracted, and we try to extract them again. So this means we have now the possibility to find some hidden file systems that is somewhere in the firmware binary blob hidden, and we can now extract it. We are doing again a Linux root file system detection, and now it doesn't matter if we have a Linux root file system detected, so a valid Linux system, or if we haven't detected a valid Linux system. Now we start up the EMBA analyzer modules, which means we are now not only able to analyze Linux systems, we are also able to analyze other binary stuff. And this means the analyzer modules, which are the heart of the whole firmware security vulnerability analysis within EMBA, are started up. And they are answering our questions like which files, how many files, which binaries, which libraries, what software components are in it, what kernel version, what software versions at all, and so on and so on, privileges, configuration files, and so on and so on. All of these questions getting answered now by our analyzer modules. So now we're talking about a feature that which we introduced in August this year, the system mode emulation engine. And this system mode emulation engine is more or less the idea that we are able to boot up the firmware of the embedded device until a state where we can use it like the real embedded device. So for live testing. This means that we are moving away from the static only approach to a more dynamic approach. So we call this hybrid firmware analysis. As we use emulation for this, we need to talk a little bit about emulation and what emulation is at all. So, according to Wikipedia, in computing, an emulator is hardware or software that enables one computer system, which is called the host. This is the system from the analyzer. This means that this is the system where EMBA is running on, typically Ubuntu or Kali Linux. And this system to behave like another computer system called the guest. The guest is the firmware of the embedded device. And an emulator typically enables the host system, so our EMBA system, to run software or use peripheral devices designed for the guest system. So these are designed for the firmware, for the embedded device. And we are running it on our host system, on our Kali or on our Ubuntu. So that's the idea. But for emulation, there are two different types of emulation available. First of all, there's the user mode emulation. User mode emulation is used by EMBA for at least the last 2 years. And it is more or less that the emulator is able to run simple programs that are designed for a different architecture for the embedded device on our host system. And we are using this for generating quite complete software bill of material. So we are using this to create an overview of the used software components, including the whole version information. And with this, let's say, software bill of material, we can now extract further data from other databases like a CVE database. With the CVE database, we are now able to find all of the vulnerabilities that are in a special software component. And with the vulnerability details, we can now query further databases like an exploit database or the Metasploit database. And so we are going down the way from software bill of material to a vulnerability bill of material, and then to a known exploit bill of material. So the second mode of emulation is the system mode emulation mode. So with the system mode emulation, we are trying to boot up the firmware to a state where we can interact with the firmware, with the firmware. Like in the idea is to interact with the firmware like with the original embedded device. Definitely, we will face with a lot of challenges. For example, we are talking about different architectures. The kernel is optimized for the embedded device, but not for our emulated environment. The file system is now extracted, so we need to repack it in a way that the emulator can work with it. And the peripherals, they're just not there. And yeah, we will face with a lot of different other issues and aspects of the original embedded device and the emulation. But nevertheless, in I think 2016, there was a project called Firmware. They have first shown that it is possible to completely automate system mode emulation. And they were able to emulate quite a lot of devices completely automatically. A few years later, 2020, Firmware, the successor, has shown that on the base from Firmware, it is quite easily possible to extend the emulation capabilities massively. And yeah, the problem now is that both projects are not actively maintained anymore. So we have decided to completely re-implement it into EMBA modules. And during this re-implementation, we have found some possibilities for optimizations. And so now we are able to maintain it by ourselves as EMBA modules. We can extend it with further EMBA modules. So if we want to do some further checks, we can just include some new EMBA modules quite easily. And there are a lot of improvements now already in place and some new modules like a completely new Metasploit integration that we can now use during our full system emulation. So I know you all love benchmarks like we do because it's a good possibility to verify the re-implementation. And the people on Firmware, they have released the whole test set of around 1,100 firmwares. And they tested it against Firmware. And for example, they've seen that in nearly 30%, Firmware was able to boot up the system to a state where it was reachable via ICMP, so via ping. Firmware has increased this to nearly 90%. So in 90% of the firmwares, they were able to reach the device or the emulated device with a ping. If we are talking about some services, some network-based services, Firmware was able in 16% to boot the device to a state where we were able to communicate with some network service. Firmware has improved this rate to nearly 80%, which is a quite high number now. And the re-implementation as EMBA modules, you can see it on the dark green fields that nearly everywhere we found some improvements. And the ICMP rate we increased to 98%. And also the rate where we were able to communicate with some network service, we increased it to 90%. And 90% success rate. I think now it's time to include such mechanisms into an automated firmware analyzer. So one quite new feature that we introduced a few weeks ago is now the Metasploit integration. So during our full system firmware emulation, we are now able to automatically test all the Metasploit exploits against the firmware, which is now running. And at the end, you can see the result in our final aggregator, which is the reporter. So you can see with one view that the system we were able to emulate it successfully. We were able to reach it via ICMP, via Nmap, and finally we have exploited it. And the Metasploit module by itself, you can see that we have an active session. We got this active session during our emulation. So we actively exploited the device, fully automated during our firmware analysis. So this means now it's time for a short demonstration of EMBA. So now let's move on to the demonstration. So now you can see my desktop from my Kali system, where I will now install and use EMBA. First of all, where to get EMBA? Just go to our GitHub repo. It's under github.com e-m-b-a, and you will find there two different projects. On the one hand, there's EMBA. EMBA by itself is the core, the scanning engine, let's say. And then you can find the new one, Embark. Embark is the, let's say, enterprise-ready web user interface for EMBA. So you can use it via multiple users, you can upload your firmware, you can organize it quite handy in a web environment. But now let's move on with EMBA. So the EMBA repo is quite easy. You have some basic information directly on the front side, and you can also see the installation instructions, which are quite easy. So just clone the repo, change into the directory, and perform a default installation with -d. So let's do it. So we are copying just the path, do a git clone, which is quite fast. Then we are changing into EMBA, and you can now see the usual directory structure here. What's probably interesting for you? First of all, the installation command, which we will see in a few moments. And after the installation, or during the installation, the installer will download a Docker image. And the Docker image is well prepared for EMBA with all of the different tools and components that we need. And for starting the analysis tasks, then you can use the EMBA script. With the EMBA script, let's just do it. Now we can start with the installer. And we've seen before on the GitHub repo with -d. And I will stop it now because I already have it installed on my machine. But usually the installer will run through the installation process, will download the GitHub or the Docker image and set up some basic tools on your host, which means the CVE database, for example. That's quite handy because you can update the CVE database on your host quite easily, and all of the other tools and dependencies are maintained by us. So now let's go to my installation. That's already there, and we can just take a look at EMBA and all of the different possibilities or command line switches. I've mentioned before that one command line switch is enough to start EMBA. This is the firmware path. But usually, if you are just configuring EMBA with the firmware path, then there is no multi-threading activated, there is no web report activated, and so on and so on. So normally you will use three parameters: the firmware path, the log directory where should the results stored. And then EMBA has some nice feature, which we call profile support. I'm just looking for it. I don't see it here. Yeah, we have it here. And we have some predefined profiles in the scan profiles directory. For example, the default scan. Usually I use the default scan emulation, which means that also the system mode emulation tasks are performed. And finally, there's also a full scan profile, which takes a little bit longer, but check it out. And now you can start EMBA just with EMBA -f, the firmware, which is downloads. In this case, we are using this DRR firmware. Then let's say we log to the downloads directory, EMBA logs, and then we use the profile scan profiles full scan, which is using all of the modules from EMBA. And if we press enter, EMBA starts with a health check and fails. You can see it that the Docker interface is not up and running. So let's restart it and then try it again. So now EMBA is starting up with the health check, and it tests some things that it needs on the host. For example, the Mongo database, the Docker interface, so the network environment, also the privileges that we have. So it checks, for example, if you're in the Docker group, and then you're fine. And for example, the CVE search database, which is needed for the identification of all the known vulnerabilities, and further tasks like identification of all the exploits, and so on and so on. So now EMBA is starting up, is doing some downloads of needed things, and then you can see it now. EMBA does some basic analysis of the firmware file, some visualization, and now you can you're probably familiar with binwalk. Now EMBA is using binwalk for the basic extraction. And yeah, we can now stop this process because I've prepared the results already, and this test or this firmware analysis task will need quite a while. So let's stop it now. And the last thing that you will probably see from EMBA is the aggregated overview of the results. So you can see it. You can see some basic information of the firmware, like what is the EMBA command that was used, which architecture was identified, which Linux kernel, and so on, binary protections, and so on and so on. But the more interesting stuff is now, as we have used one of the default profiles, we also have a web report. So we can go directly to the browser, and you can see the web report. It looks quite familiar. It looks the same as on your command line interface. The interesting thing now is that it's everything interconnected. So you can just click on something and you get to the right module that has produced the output. You can, for example, you can see the binary protection mechanisms. You can see the top 10 list of which binaries you are using most heavily string copies or call to systems. And you can get an overview of the software bill of materials or software inventory, the components with versions, how many CVEs have we found in this version, how many exploits or proof of concepts have we found, what is the source. In a moment I will show it to you. So you can see source is user mode emulation, static detection, or for example system mode emulation. And you can see here there's multiple CVEs, multiple exploits. Identified via system mode emulation means that it is available via the network. And another quite interesting thing is there is one version detail that is currently unknown, but we have an exploit, and this exploit is Microsoft verified, which means we were able to completely automate it for automated exploitation during our firmware analysis tasks. And you can see it also here. There is another overview. System emulation was successful. It was booted, we detected an IP address, the system was reachable via ICMP, we did a port scan on it, and we were able to exploit it. So now, let's have a quick look at I would say we take a look at the system mode emulation engine now. You can see a lot of things, a lot of information. So we are preparing the whole environment completely automatically. We said we boot it up during the emulation. Let's scroll a little bit down. We try to identify if the system was booted up, which services were started, what was the network configuration of the device. We create different possible network configurations that we want to test during the next steps, and then we try to ping it, and you can see the system is reachable via ICMP, and then we try to perform an Nmap port scan on the detected services. So you can see that port 23 is, for example, open, port 80, and at the end you can also access the whole QEMU logs, so you can verify what was happening on the device with some interesting highlighting. And you can see that network services are available. So the Nmap port scan has found different network services. You can download the emulation archive for further verification, or you can just walk through the report. For example, you can see a screenshot now from the web interface. And we can walk through this a little bit further. Give me a second. Here you can see the feature that I've mentioned before. This is the Metasploit verification, and you can see that there's a vulnerability verified, D-Link UPnB exec no-auth with CVE details. And during the live testing, we are doing two things. First of all, we are using the check functionality of Metasploit. And if this check functionality says, okay, the target is vulnerable, then we're fine, okay. If this check function says, okay, I don't know if it's vulnerable or not, then we are trying to exploit it actively. And via this active exploitation, we probably get a shell like this. And then we know. So we now know the real world risk of this firmware, not just the theoretical risk of there's a software component with this or that vulnerability. Now we know, okay, this vulnerability, we can exploit it. This is a real world threat for the firmware. And at the end, we can go back to our main dashboard of the report, and we can move on. For example, we can perform the further teardown of the different software components, and so on and so on. So thank you very much for your interest in EMBA and in firmware security at all. So right now you should definitely go to our GitHub repo, download EMBA and start analyzing at least your IoT environment. And we have another quite interesting news for you. We released version 1.2.0 now, and we call it the London Calling Edition. So check it out. Analyze firmware and make the Internet of Things a little bit more secure. Thank you very much.